Hey guys, welcome to this video on static friction. In this video we're going to be taking a look at the equation for static friction maximum and figuring out how we can make calculations and predictions. Also, more importantly, what all the different terms mean. So I'm going to start with an example here where I have a box, and this box is very heavy and I'm pushing it and it's not moving. So if I draw a free body diagram here to analyze the situation, I have, of course, vertical forces, and I have an applied force because I am trying to move the box. But for whatever reason, the box is not moving, which means that the net force, specifically here horizontally, is going to be equal to 0, which means there has to be a force going backwards in this direction that is equal in magnitude and opposite in direction, and this we are labeling as the frictional force. We're going to put an S here to specify that it's a static frictional force, meaning that this object is at rest, rather than if I put the kinetic subscript here, or K, that would imply that this was at a constant velocity. So this helps us define that the applied force is the same as the maximum static frictional force here in this case. But let's say for our example that it's not the maximum value. So let's add, I really need to move this box, so I push a little bit harder. So I'm going to draw another diagram down here. It's still the same weight box. The ground is still pushing up with the same magnitude of force. But in this example now, we are going to show that I'm pushing a little bit harder because I really need to move this box. And this applied force now is greater than what it was originally, but the box still doesn't move. So we say that the net force is still equal to 0, meaning there must be another force back in this direction that is equal in magnitude, opposite in direction, and it's still going to be the static friction value, but it has now increased. It is matching the applied force every time. Now there isn't really a relationship between these two variables specifically. In the specific experiment there is. As the applied force gets bigger, the static frictional force gets bigger. But they don't match, they don't have a relationship beyond that. At some point I'll reach the maximum static friction, and at that point the box will begin to move. And this will change from static friction to kinetic friction, and the value will change considerably. So we can see that if we were going to sketch ourselves a little graph over here between the applied force and the static frictional force, we would see that as the applied force increases, the static frictional force increases, but then we reach a tipping point and we get this dropping off. And this point right here is known as the maximum static friction. And at that point, we can actually make some specific calculations that have to do with more than just the applied force. In other words, there are factors that determine the amount of static friction maximum that you can have that are beyond just what your push is. So this maximum static friction value here is what we're going to be focusing on for the rest of this video. Now, from the lab activity that we did where we tried to vary the normal force and see how the static frictional maximum changed, and we must make sure that we put this value on here, the relationship between those two generated an equation that we were able to use that was pretty simple. It came out as a linear function. And so if I sketch this graph over here, what I found was that if I applied force to an object, the more force I applied, the more static friction there was until I hit the tipping point where it became the maximum static friction, at which point I recorded the value of the maximum static friction corresponding to normal force, and I placed that value on a graph. So I'm going to have a normal force as my horizontal axis and maximum static friction as my vertical axis. What I did then was add more mass to the box and found the new maximum value that could be achieved and plotted that point. We continued adding more mass to the box, which of course is going to increase this normal force value because we keep adding extra vectors pointing down, so the normal force keeps increasing, which means that you can have a new maximum static friction achievable for the greater amount. And we kept doing that, and we got a direct proportion, something that looked like this. And from this equation, we could say that the maximum static friction, I'm going to put here a subscript max, equals some constant. Let's say that our slope came out to be 0.22, just for this example, times the normal force. We saw there was a direct proportion between normal force and maximum static frictional force. Now, why do we have normal force here and not force weight? Well, I'm going to take you over to an example here on the side and take a look at the relationship between normal force and maximum static friction rather than weight force. Because you might think, well, a heavier object is going to have more static friction when I try to push it, or a greater maximum value. And that is true, but it's not because of the force of weight, it's actually because of the normal force. Those just happen to be the same thing on a flat surface. So let's take a look at this. We have an example where we have a box or a wooden block, let's say, being pushed up against a wall. And so what I'm going to do here is I'm going to show that I have an applied force pushing the block into the wall, which means there will be a normal force back from the wall on the box. And the force of weight is going to put straight down here. And in order for this box to stay at rest, I'm going to have to make sure that I have enough friction pointing upwards, like this, to keep this box at rest. And this is a static frictional force. Now let's say I push in with a certain amount of applied force. Well, the normal force responds with the exact same amount. The weight of the box has not changed. Now let's say this isn't enough, and what happens is the box begins to slip downwards. And that means there would be a velocity down, meaning this value over here was not large enough, the static friction, to hold it at rest. So let's say I wanted to keep it at rest, so I need to have a net force that's equal to 0. I have not really many options except for pushing harder into the wall, so I'm going to go ahead and show that by adding an extra tally mark from the first example here. So I have a force applied, meaning the normal force now has increased to match again my applied force. The force weight still happens to be the same thing as it was before because I haven't changed anything about the box. And now the static friction will have increased based on how hard I pushed. And this actually makes sense. If you rub your hands together lightly, as in this first example here, versus if you push your hands together more tightly and rub them together, you'll feel more heat. And the heat that's being generated is a result of the static frictional force, or the kinetic frictional force really in that case. But the whole point is that surfaces pushing harder together is represented with the normal force. So it's not really the weight that has anything to do with the amount of static friction maximum, but rather the normal force. So when we think of this equation as what truly affects the amount of maximum static friction that two surfaces exert on one another, it's really how tightly the surfaces are pushed together. So what we want to put here is, think of this rather as surface contact rather than as the weight of the object. Now, in flat surface examples, as I said before, the weight of the object is the same as the normal force, and that's why sometimes we misinterpret and think of the static friction as being determined by the weight rather than the normal force. But it's really to do with the surface contact, which is what the normal force is defined as. Now, to wrap up this video here, what I want to talk about is this very last term, which is this right here in the middle, 0.22, which is defined as the coefficient of static friction. And this term sounds more fancy than it truly is, but what you can think of this term as being is a numerical representation of the surfaces in contact. So what do I mean by numerical representation of the contact surfaces? Let's say in this example with the box being held up against the wall. Let's say I couldn't push any harder without breaking the wall. So I needed to figure out a different way to keep the object at rest against the wall. Well, what I might do is change the surface that's in between the contact space between the box and the wall. This is the surface interaction, and the surface interaction, not necessarily how hard I'm pushing in terms of the surface contact, that's the normal force, but actually what the two surfaces are that are in contact. So for example, if I were to replace this box with a block of ice that had been wet on one side, it would be very slick. And what that would mean is there wasn't very much static friction. Even if I'm pushing as hard as I was in any other case, the static friction maximum would not be enough because this coefficient of static friction, which is the numerical representation of the contact surfaces, would be decreased. So for example, I could have a combination of, let's say, ice and metal. Well, ice and metal, particularly wet ice and metal, might have a very low coefficient of friction. Coefficient of friction is symbolized with the Greek letter mu, which to some people looks like a U with a tail on the front, and some people it looks like a more cursive M. And so we would have many different experimental values for different combinations of metal. Something like sandpaper and wood would have a much higher coefficient of static friction. And so you can see that this number in the middle here is going to have a few different important descriptors or properties. It's considered to be a laboratory experimental value. It's also considered to have a different amount of numerical value depending on what the surfaces are in contact. And in addition, it's going to be unitless. And we'll take a look at that in another video, more information once we start looking at the kinetic friction.